So, today we're diving into something truly monumental in science, the quest to build a complete, working simulation of a human cell. We're talking about creating an AI-powered digital twin that could literally change medicine forever.
Just think about that for a second. What if we had a virtual lab on a computer where we could test any drug or watch any genetic mutation play out long before it ever gets near a real person? This really isn't science fiction anymore. The goal here is to create a perfect digital copy of the most fundamental unit of life, the cell. Because at the end of the day, that's where health and disease really begins.
So you might be wondering, why haven't we done this already? Well, it's because for all of our amazing biological knowledge, the cell's inner workings are still, in a lot of ways, a total black box. We can see what goes in and we can see what comes out. But figuring out that incredibly complex chain of events inside, that's a whole other story.
And the complexity inside that box is just immense. I mean, you've got countless molecules all interacting at the same time, where one tiny change can set off this massive, unpredictable ripple effect through the whole system. And these things are happening on timescales from picoseconds to decades. This complexity has been a huge roadblock for medicine. It's the reason we struggle to know exactly how a new drug is going to work or why a disease unfolds the way it does.
But here's the good news. That roadblock is starting to crumble. Right now, there are two massive parallel revolutions happening in science and tech that are finally giving us the keys to unlock that black box. And here are those two keys. On one side, you have the data explosion. Thanks to these incredible technologies, scientists call them omics, that map out our genes, our proteins, everything, we are charting the cell's parts at a truly exponential rate. But, all that data is just noise without the second key, the AI revolution. We finally have AI that's powerful enough to swim through that ocean of information and find the hidden patterns, the actual rules that run the cell. It's perfect, really. One gives us the raw material, and the other gives us the engine to understand it all. And to give you a sense of the scale we're talking about, just one data repository, the Short Read Archive, holds over 14 petabytes of biological data. That is more than 1,000 times bigger than the dataset that was used to train the famous AI, ChatGPT. The amount of information we have to work with now is just staggering.
And we're generating it at a breathtaking pace. I mean, think about this. Less than a decade ago, analyzing just one single cell was this heroic, massive effort. Now, we've gone from those early methods in 2015 to profiling cell surfaces in 2017, and now we're generating these gigascale datasets with hundreds of millions of cells, all specifically designed to be used by AI. The speed of this technology is just unbelievable.
So what happens when you fuse this explosion of data with the raw power of modern AI? Well, you get the foundation for building a true digital twin of a living, breathing cell.
This is what scientists are calling an AI virtual cell, or AIVC. And let's be really clear about something. This is not just a static map. An AIVC is a dynamic simulator. It's a model that actually learns the rules of biology straight from the data, and then it can simulate how a cell is going to behave and change over time, or say, in response to a new drug.
Now, to build these models, you need absolutely frontier-sized datasets. Take Tahoe 100M, for example. It's a landmark open-source dataset from Tahoe Therapeutics. It contains detailed molecular profiles from 100 million individual cells after they were treated with thousands of different drugs. It is one of the biggest biological datasets of its kind, and it was created for one reason: to train these incredibly powerful new AI systems.
Okay, so what can this digital twin actually do? Well, first, it can predict. It can forecast how a cell might react to a drug it's never seen before. Second, it can simulate. It can model processes over time, like watching a stem cell turn into a heart cell, or watching a healthy cell turn cancerous. And third, it can guide our research. We can run millions of experiments in silico, which just means on a computer, to come up with smarter ideas and make the real-world lab work way faster and more efficient.
And this isn't just some theoretical exercise, some cool idea for the future. This approach is already giving us insights that could absolutely revolutionize medicine. We're talking about turning decades of discovery into days of computation.
Let me give you a real-world example. Let's talk about a drug called Saquinavir. For decades, this drug was a cornerstone of HIV therapy. It helped turn what was once a fatal disease into a manageable one, and it saved countless lives. But there was a hidden danger. A really serious one. After more than 20 years of being used by millions of people, doctors finally put the pieces together and realized the drug carried a serious risk of causing dangerous heart rhythms. It took 2 decades of real-world human experience to find this link, and eventually, the drug had to be pulled from the market.
Okay, now here's where it gets absolutely incredible. Researchers took the data for Sequinavir and fed it into an AI model that was trained on that massive Tahoe 100M dataset. The AI looked at how cells responded to the drug and it correctly predicted its toxic heart effects. It saw that Sequinavir was making cells act just like other drugs known to cause heart problems. As Dr. Johnny Yu said, the AI found in a single analysis what took the entire medical community 20 years to figure out.
And the potential here is so much bigger than just finding side effects. This is about changing how we fight our most complicated diseases. Think about cancer. These models could help us understand the complex 3D world of a tumor and see exactly how cancer cells are hiding from our immune system. This could lead to truly personalized oncology, where we design a treatment based on a digital twin of your specific tumor. And beyond cancer, we could engineer cells to fight things like diabetes, designing them entirely in a simulation before we ever make them in a lab. It just fundamentally changes the game for drug discovery and precision medicine.
Now, as exciting as all of this is, we have to be realistic. Building a truly comprehensive, predictive virtual cell, well, that's a grand challenge. There are still some major hurdles we've got to clear. And maybe the biggest challenge of all is this. The AI virtual cell can't just be another black box, right? It's not enough for it to just predict what will happen. For this to be really useful for science, it has to tell us why it happens. It needs to lay out a testable, step-by-step chain of events. Basically, it needs to give us a theory of the cell that scientists can then go and prove in a lab.
And getting there is going to take a global effort. We still need more data and more varied kinds of data to see the whole picture. We need absolutely massive computing power on a scale that public science has rarely ever seen. But you know what's most important? This is way too big for any one lab or any one company to solve. It demands an open, collaborative approach from the entire scientific community, sharing data, creating common benchmarks to see what's working, and all pulling in the same direction.
So that's the ultimate goal, a model that doesn't just predict biology but actually explains it, a testable theory of the cell that runs on a computer. And that leaves us with a really fascinating question to think about. Once we finally have it, what disease, what great medical mystery are we going to solve first?